Hello APC Mechanics students in Unit 4 System of Particles and Linear Momentum, Class 9, 4.3 Conservation of Linear Momentum, Part 5. Section 1 Inelastic Collision, Explosions. One specific type of collision is when a body explodes into two or more fragments. This collision is classified as inelastic collision as the system gain kinetic energy. So this is the first time where we see the system as a whole gain kinetic energy due to an external source, as we shall see. The source of energy might be chemical energy or elastic potential energy. In this section, we will demonstrate or anticipate the following scenario. Consider an object initially at rest that explodes and splits into two fragments of masses m1 and m2. Now, what causes the system to explode into two fragments? So initially here we might have a spring which is compressed, or a type of chemical energy that might explode. Directly after the collision, the fragments m1 and m2 acquire speeds v1 and v2 respectively. Then the speed v1 is to the left and the speed v2 is to the right. We can apply the conservation of linear momentum if we consider our system to be isolated. Then P initial is equal to P final. Initially, because the system was at rest, which means that the total momentum is 0, and finally we have two momentums given by P2, which is positive, and minus P1, which is negative. Then that would be m2v2 minus m1v1, and that would be m2v2, which is equal to m1v1, because initially the momentum of the system is 0, which means that after collision, even if this fragment has a momentum P1, and even if this fragment has a momentum P2, but according to the cancellation effect, both of them should cancel up to 0. Then we can make use of the following relation m2v2 is equal to m1v1 in either to solve for one of these variables. If we suppose that the speed v2 is unknown, then it's given by v2, which is a fractional mass, multiplied by v1. Now for the rest of the video, we're gonna solve some exercises. A balloon of mass capital M is floating motionless in the air. A person of mass less than m is on a rope ladder hanging from the balloon. Now we have a balloon of capital mass M and we have a person of small mass m, let's suppose. The balloon and the person, we suppose that they are floating motionless in the air, so the total linear momentum of the system is conserved, which is 0 because it's motionless. Now if the person is climbing up with a mass small m and speed v, then we expect, in order to have the cancellation effect, in order for the linear momentum to be conserved, that the balloon will go down with a momentum given by capital M multiplied by capital V, and they're asking us for the capital V. Now the thing is that initially, before the motion, it's motionless, so the total linear momentum of the system is 0, which is conserved, and that would be equal to M multiplied by V minus capital M multiplied by capital V, because they are in opposite direction, which means that MV should be equal to capital M multiplied by capital V. That would be for the person and that would be for the balloon. In order for this quantity to be conserved, this equality, if the mass M is greater than the small m, so this is big and this is large, which means that the small speed would be big, and the big velocity should be small in order for the product to be conserved, which means that the balloon will move downward with a speed less than v in order for the product m multiplied by v to be equal to m multiplied by v for the person. Now exercise 2. A person holds a portable fire extinguisher that ejects 1 kilogram of water per second horizontally at a speed of 6 meters per second. What horizontal force in Newton must the person exert on the extinguisher in order to prevent it from accelerating? So in order to prevent acceleration, both forces exerted by the person on the portable fire extinguisher and by the force exerted by the extinguisher on the person should be equal. Now let's find this force. Now the force is given by dp by dt, which is an average force given by delta p divided by delta t, let's say, which is m delta v divided by delta t. And let's recall that p is given by m multiplied by v. For that, delta p would be given by m delta v. Now m delta t represents mass per time, and we have 1 kilogram per second, so that would be 1 kg divided by second. multiplied by the variation in speed. Suppose that the water is being ejected from rest, then if this is the final speed, then delta V, or the variation in velocity, that would be 6 minus 0, which is 6 meter per second, then multiplied by 6 meter per second, and that would give you 6 kilogram meter per second square, which is equivalent to 6 newtons, which makes B to be the correct answer. Exercise 3. A railroad car of mass 1,500 kilograms rolled to the right at a 4 meter per second and collides with another railroad car of mass 3,000 kilograms that is rolling to the left at 3 meter per second. The cars stick together. Their speed immediately after the collision is what? So we know that if this is a free response problem, we should start our solution with the conservation of linear momentum statement, because the system is isolated, then P initial is equal to P final. Now after collision we have one system which is given by the sticking of m1 plus m2 multiplied by capital V that we wish to find. So this is, let me say, m1 with a speed v1, and that would be m2 with a speed v2. So in this case the momentum is given by, if this is to the right, then m1 v1 minus m2 v2, and if you isolate for capital V, then capital V is given by m1 v1 minus m2 v2 divided by m1 plus m2, which is 1500 multiplied by 4 minus 3000 multiplied by 3 divided by the total mass, which is 1500 plus 3000. Now plugging that fraction on the calculator, we're gonna get 2 over 3 meter per second. I think the answer would be negative, but since they're asking for the speed, then we're gonna choose 2 over 3 meter per second. Exercise 4. A toy spacecraft is launched directly upward. When the toy reaches its highest point, a spring is released and the toy splits into two parts with masses 0.02 kg and 0.08 kg. Now when the toy reaches its highest point, so we are at a point in space in which the momentum is 0 because the speed is 0 due to the highest point. Now it will split into two fragments respective. Immediately after the separation, the 0.02 kg part moves horizontally due east, so that this is the east, north, south, east, west. This is 0.02 kg, and that would be moving to the right with a mass of 0.08 kg. And if you notice carefully, this is of greater mass, then it will move with a less speed, and this is of less mass, it will move with a greater speed, such that the product of this mass with this speed is equal to the product of this mass with this speed, and taking into consideration the cancellation effect. A resistance is negligible. True statements about the 0.08 kg part include which of the following? It could move north immediately after the spring is released, so we know that the 0.02 kg would move to the east. This is sure. Now I have represented this to be moving to the west, because we know that in order to have the conservation of linear momentum, they should be directly aligned to each other. Now it could move north. No, that's wrong, because we know that if one of the fragments move east, then the other one would move west, especially take into consideration the fact that it reaches its highest point. So before splitting, it has 0 speed, and it's moving upward, so there is no horizontal motion. Now it takes longer to reach the ground than does the 0.02 kg part if we're neglecting a resistance, as it's claimed here. So both masses, since they are released from rest vertically, not horizontally, they will reach ground with the same speed, which means this is also wrong. It strikes the ground further from the launch point than does the 0.02 kg part. No, that's wrong, because the 0.02 kg will be launched to the right with a greater horizontal velocity, which means it will reach a point on the ground which is farther than the 0.08 kg. Alright? Now if you look at the statement carefully, they're telling you it strikes the ground farther from the launch point than does the 0.02 kg part. No, that's the opposite way around, so none of the above. Two blocks of masses M and capital M and 2 capital M are on a frictionless horizontal surface shown above and are held in place with a compressed spring of negligible mass between them. So initially there is no motion, then the total linear momentum of the system is 0, which means the center of mass of the system, which replaces M and capital M and 2M, is at rest. So the center of mass is at rest. Then after the spring will be released, capital M will move to the left with the velocity double of v, and the double of M will move to the right with the velocity v, such that the product of these two are equal and having the cancellation effect. For the center of mass, if you replace these two by the center of mass, it will be apparent that the center of mass won't move and it will remain at rest. Okay, if the blocks then are released and the block of mass 2m leaves the spring with velocity v, the velocity of the center of mass of the blocks, so they're asking for the center of mass of the blocks, we know that it would be 0 because initially before the spring pushes the two blocks, the total linear momentum of the system was 0. 3 identical disks are initially at rest on a frictionless horizontal table with their edges touching to form a triangle as shown in the top view above. An explosion occurs within the triangle, propelling the disks horizontally along the surface. Which of the following diagrams shows a possible position of the disk at a later time in these diagrams? So initially the total linear momentum of the system is 0, which means that after the explosion, the linear momentum of the system of the 3 disks should be in a way that they sum up to 0. Now the one which is true is D. It's E. Let me explain why. Because this fragment initially was at this point and it moves to this point, which means it has a linear momentum to the left. Now these two has a linear momentum. This is up left and this is up down. So up and down they cancel and they would add up to the left, having the cancellation effect with 1 to the right, which means that E is correct. D is wrong because, alright, this is moving to the right, that would be left down, that would be left up. Sorry, here, yes, as I said, left up, left down, so that would be left up, left down. But the thing is that notice that they are separated by the same distance from the triangle, and if you add up these two vectors, we would having a momentum to the left which is greater than the one to the right, which means that they don't sum up to 0. Now this is wrong because here the momentum is 0 and here the momentum is 0, and we would end up having a momentum to the right which is not 0. Similarly here and similarly here if you do the vector representation, which means that E is the correct one. Now a firecracker of mass 2m is moving at a speed v in the positive x direction. So before the collision, we have a mass of 2m moving with a speed v in the positive direction. It explodes and breaks up into 2 identical fragments, each of mass m. After the explosion, one fragments move at the same speed v in the negative direction. So that would be mv. The speed of the second fragment must be, so if this is 2m, mass is conserved and this is m, and we're interested in finding v prime, then we can apply the conservation of linear momentum. P initial is equal to P final, then 2m multiplied by v, that would be equal to minus let me say m multiplied by minus v plus mv prime, and we're interested in finding v prime. M with m with m, that would cancel, then 2v is equal to minus v plus v prime, which means that v prime is 3 multiplied by v, then which means that C is the correct answer. Exercise 8, as shown above, 2 students sit at opposite ends of a boat that is initially at rest. The student in the front throws a heavy ball to the student in the back. So initially the student sitting in the front will throw a heavy ball to the student sitting on the left. What is the motion of the boat at the time immediately after the ball is thrown and later after the ball is caught? So here we're talking about 2 phases. We're talking about the motion of the boat when the girl throws the ball, the student, and at a later time after the student holds the ball back again. Now the thing is that if the boat or the system is initially at rest, then the total linear momentum of the system should be 0. Now if the student in the front throws the ball, the heavy ball, to the left, which means that this ball acquires a momentum to the left, then the system, which consists of the two students and the boat, should move to the right with a momentum exactly equal to this. Then immediately after the student in the front throws the ball backward, the boat, which is the system, should move to the right, which means forward, which means it's either A, B, or C. Now, after the student catches the heavy ball. Now, by that, before the student at the back catches the ball, the system is moving to the right. Now, this student will catch the ball, and that would produce a momentum to the left, which is exactly equal to this momentum, because remember that what caused the momentum forward and what will cause the momentum backward is the momentum due to the ball when the student in the front throws it and this student catches it back. So it's exactly equal. So when this student at the back catches the ball, what will happen is that the momentum produced by the ball on the student will cancel this momentum, and we're gonna end up initially with the total linear momentum to be 0. Then we expect that after the catch, the boat doesn't move anymore, which makes C to be the correct answer. Now, an object of mass m is moving with a speed v0 to the right on a horizontal frictionless surface as shown above, and it explodes to two pieces subsequently. One piece of mass 2/5m moves with a speed v0/2 to the left. The speed of the other piece of the object is, so before the collision, what do we have? We have m and v0 to the right. Now, after the collision, what we would have is the following. We have two pieces. One of them is moving to the left with a mass of 2/5m with a speed v0/2. And because the mass is conserved, if one of the mass is 2/5m, then the other mass is 3/5m. And we are interested in finding v prime, which represents the speed of this fragment. Now we can use the conservation of linear momentum. P initial should be equal to P final, and mv0 would be equal to 2/5m multiplied by minus v0/2 plus 3/5m multiplied by v prime. So let me write the equation again. Okay, so here we have a minus sign plus 3/5m multiplied by v prime. Now m with m would cancel, 2 with 2 would cancel, then we would have v0 is equal to minus v0/5 plus 3/5 v prime. Now that would be v0 by, so let me just multiply everything by 5. So that would be 5v0 is equal to minus v0 plus 3v prime, which means 6v0 is equal to 3v prime, which means that v prime is equal to 6/3v0, which is equal to 2v0, and that would make E to be the correct answer. Exercise 10. A toy cannon is fixed to a small cart and both move to the right with a speed v along a straight track as shown above. The cannon points in the direction of motion. When the cannon fires a projectile, the cart and cannon are brought to rest. If m is the mass of the cart and the cannon combined without the projectile, and m is the mass of the projectile. So initially, the cart, the cannon, and the projectile, which is found here inside, which consists of the mass m plus capital M plus small m, was moving at a speed v. Then according to conservation of linear momentum, P initial would be equal to P final. Then capital M plus m multiplied by the speed v should be equal to what? Now, when the cannon fires a projectile, the cart and the cannon are brought to rest. Then the mass, which consists of capital M that represents the cart and the cannon, would come to rest, which means 0. And the only part which is moving is the projectile, which consists of the small m, would be multiplied by capital V. And we're interested in finding capital V. Then m plus m multiplied by v would be equal to small m multiplied by capital V. Then capital V would be equal to capital M plus M divided by small m multiplied by the speed v, which means that B is the correct answer. Now, exercise 11, two people are initially standing still on frictionless ice. They push on each other so that one person of mass 120 kg moves to the left at 2 meters per second, while the other person of mass 80 kg moves to the right at 3 meters per second. What's the velocity of their center of mass? Now, no need to do any calculation. The velocity of the center of mass is 0 because initially, before they push on each other, the system consisting of the two people, they are standing still, which means that the velocity of the center of mass is 0, and that would be conserved after the collision. Although one of the persons would be moving to the left with a speed of 2 meters per second, and the other person would be moving by 3 meters per second. And you can check by doing the calculation on 120 multiplied by 2 multiplied by minus 2 because it's to the left, that would be minus 240 kilogram meter per second. And the other person would be 80 multiplied by plus 3, and that would be 240 kilogram meter per second, which means indeed they're both linear momentums. They cancel up to 0, which means initially the system was not moving, which means the velocity of the center of mass is 0. Then that's it for me in this video, guys. See you soon in a new one.